Infinite Ramsey. I will go roughly in the order that I made my abstract. So I will start with something that hopefully we are all on board with. So suppose I have a graph of 6 vertices. Okay. And I color the vertices, sorry, the edges, either red, or in this case pink, or yellow. I didn't have blue. And the theorem is that for all colorings, which we can think of it as, let the set be G, okay, and this is how I'm going to denote it. G choose 2, okay. So you might have seen the binomial notation of n choose k. Here I have a set in place of the top element, and this is the set of all 2-element subsets. So if I have a coloring from G2 to red, yellow, then I can always find that either there will exist 3 vertices, maybe I'll just call it a monochromatic red triangle, or a monochromatic yellow triangle. So please raise your hand if you've seen this theorem and it's proved. Okay, excellent. I will go over it anyways. So let us pick one of the vertices. Then by the pigeonhole principle, what do we know? We know that there are 5 other guys, so at least 3 of them must be one of the 2 colors. So let's suppose that 3 of them are red. At least. And then what can we say? Well, there is one triangle here. If any one of these edges is red, then we get a red triangle. If not, then all of them are yellow. So we get a yellow triangle. So we have proven, in this case, that R33 is equal to 6. Technically, I didn't prove that it's bigger than 5, but I need that as an exercise. Okay. Now, we go to the infinite Ramsey theorem. So let me set some words here. So I'm going to call these a 3-clique, which means a copy of the complete graph on 3 vertices. In general, I will be referring to k-cliques. So k for clique. But for the statement of the infinite Ramsey theorem, I actually don't need this. So here's the statement. It is that I have a coloring on all size 2 subsets of n. Okay, so you can think of an infinite graph with, in this case, red or yellow edges between all of them. And every edge is some color. Then there exists an infinite subset A, which I'm going to denote with this symbol. The bow tie means infinity. Then exists this set so that C restricted to all size 2 subsets of A is constant. Or in other words, in the graph theoretic language, I can find an infinity. Okay, a monochromatic infinity. Does the statement make sense? And this is also it is identical to this proof. I'll just redo the proof. So let's choose one of these vertices. Okay, because we're working with subsets of the natural numbers, we can actually have a canonical choice by choosing the minimum. So we can do this. And of its edges, infinitely many of them must be one or the other color. So let's suppose that infinitely many are yellow. I'm going to draw this as a yellow vertex, and then this yellow region here. And everybody here, in this restricted portion of the graph, so that there is a yellow edge between it and the chosen point. Does this make sense? Okay. So there will be other edges out here who were unfortunately deleted because they had the crime being the red edge. So we forget about those guys and focus only on these yellow ones. Now in this set, we can choose a vertex, say the minimum. Okay. And by pigeonhole again, there must be infinitely many of one color. Let's suppose it's red this time. So this guy will be red, and now everybody in a smaller subset will be such that all the edges are red. And we can continue like this. So let us choose another one in this thing. Let's do this guy. And then let's suppose that all of its neighbors that are still within this thing. Okay, remember there are infinitely many points in each of these bubbles. I can say that it is going to be connected to infinitely many points in. Does the construction make sense? At each point, I choose a point and restrict my attention to all of the other guys in the previously restricted sets, so that the edge is of the color that there are infinitely many. Now what? And continue. At the end of this process, okay, I can generate however many I want. A1, A2, A1 prime, A2 prime. To get an infinite sequence, A1 prime, and so on. And now we pigeonhole one last time. Each of these guys, I'm coloring a certain thing. So this one is yellow, this one is red, this one is red. Okay. So if I pigeonhole again, pigeonhole one last time, infinitely many are the same color. And let's suppose, for sake of illustration, that it's yellow. So I get a bunch of these guys. A1 this time, A2. And my claim is that the edge between every single one of them must be yellow. I think this is already clear, but why is that the case? Claim is that take any yellows, then the edge between them is also yellow. Why is that? Well, it's because one is in the subset of the other. Okay, and already by construction of the subset or this bubble, there's a yellow edge between them. So because of this sort of process where I keep iterating inside, I can guarantee that these things sort of form a chain. And so any two will be in the same chain as each other. And then one is further along, and so it's going to be good. So this is the infinite Ramsey theorem for H equals 2. I will explain why I chose the word H in a minute. Now I'll talk about the finite. Maybe it's a little weird to go in this order, but hopefully you'll see that in this infinite case, the pigeonhole was easy, because every time I pigeonhole, infinity over 2 is infinity. Okay, so I say that at least, half of them are of a certain color, then that's still infinitely many. Right? But in the finite case, I'm not so lucky. My claim is that the same proof holds. But pigeonhole only to thinking a house. Okay. And unlike the situation where infinity divided by 2 is still infinity, I still actually have to divide by 2 in the finite case. Okay. So in this case, every single one of these procedures, I have to cut down by half. Okay. So taking this subset, I can only be sure that there are at least sort of n over 2 points in this subset. And every time I do it, n over 2, n over 2, n over 2. And so at the end of the process, if I want to find a Higgs, you can think of it as you have to have like k times on the order of k times. And so I get actually that for all k, which is the size of my desired clique, there exists n less than like 2 to the 2k in this case, something like this. Then running the same proof of pigeonholing, then I arrive at the fact that indeed every coloring of this, there must exist size k a such that the coloring is constant. In other words, I get a monochromatic K clique. So I started with this most simple example of just pigeonholing on these 6 vertices, but you see that in all 3 of them, the proof has been the same, right? It's been literally the same proof every time, except I just am more careful with the quantifiers over here, and I have more bubbles over here. Okay. Now, instead of 2 here, I can bump up. Okay, I can also bump up to h, where h is the sort of order of the hyperedge. So instead of dealing with graphs, I can deal with hypergraphs. So I can generalize to hypergraphs, where each edge is no longer just between 2 vertices, but an edge is now something that sort of encapsulates 3. So we can think of an edge as a little tube like this. This is a 3 edge or 3 hyperedge. So the Ramsey theorem for general H is if I have a coloring from NH, okay, this is a hypergraph with H hyperedges, where H hyperedge just means each hyperedge has H guys in it. And any coloring like this, there exists a infinite in N such that the coloring is constant. So same business. And my claim is that this actually is not much harder than the infinite Ramsey theorem. Okay, sorry, in the H equals 2 case. Why is this the case? Well, again, let's start with a chosen vertex over here. I have my hypergraph, infinitely many guys indexed by the natural numbers. Okay. And I have a hyperedge. Or rather, between every 3 vertices, I have a hyperedge. Okay, that is colored either red or yellow. And now what do? I just take the rest of them, ignoring this guy, and each hyperedge of a given color reduces to an actual edge of the color. Right? So this hyperedge, I can now, in this restricted setting, give the color of a 2 red edge. And this yellow one, I can give the color of a 2 yellow edge. So this subset now is of the setting of the H equals 2 Ramsey theorem. Okay. So what does the Ramsey theorem tell me? It tells me that there is an infinite clique inside here of the same color. Okay. So I'm going to call this, suppose the infinite clique in question, H2 Ramsey, gives me, say, a yellow clique. Yellow clique. Oops. And then I just draw the exact same picture as before. This guy is now colored yellow. Okay. First colored vortex. And now the bubble is there. And all the guys in here, of which there are infinitely many, are such that there's a hyperedge, or in this case a 3 edge, that connects to this guy. Of course, there might still be the issue that in between of the guys strictly in the interior of the bubble, I get a red hyperedge, right? But this is exactly the same problem here, right? There could be wrong color edges in here, just like there are wrong color hyperedges. But you just do the same thing. You choose a guy, you get a picture like this, you run the H equals 2 Ramsey theorem, you get a monochromatic, picture so that you can draw the next dot with a bubble. Just repeat. And so you can see that the same proof will actually work also for the finite case. Okay, but instead of having a single exponential 2 to the 2k or something, you just keep powering your exponentials, right? Because each time you are using the Ramsey theorem, so each time you need something of that size in order to apply the H equals 2 Ramsey theorem. And so you get just towers and towers of exponentials. Yes.
Why large numbers, like John's number here in Ramsey theory proves.
Yes, we should not be surprised, therefore, that truly monstrous functions start showing up in these things.
In general, the order of this will be like at omega is that faster pair.
Perhaps. I don't know for sure. I might say something about the Paris-Parenting theorem at the end, but I will leave that for the end. Good. So that is the infinite Ramsey theorem for all H. Right? Can anybody predict what's the infinite Ramsey theorem? Exactly. I just take H to be infinity. Okay. Unfortunately, it doesn't quite work. There are, cursive constructions using the axiom of choice, in which you can build something that just doesn't work. But in a certain sense, for nice colorings, it does work. And that is the subject of the infinite Ramsey. So let me go to the infinite Ramsey. Okay. So good. I do not even have to erase too much. I will try to be cute in writing my proofs. Okay. So I will be reusing many things. So the infinite Ramsey theorem naively is the following statement. And as I said before, this is false. But to figure out what the true thing is, I will end up returning to the infinite Ramsey theorem again. I will prove it differently, with a proof that now does generalize. The proof that you saw previously does not behave well as H goes to infinity. It is by induction on H, so necessarily you can't get there. But let's see. Before I do that, I should give you a visual for N, which remember is the infinite substance of N. Okay. So you can think of this as in bijection to the increasing sequences of N, infinite sequences of N. Okay, so these are the sequences in Because any subset I can just order, and I get an increasing sequence. Okay. Actually, yes, and this is the infinite sequences. And for this picture, I can draw the following. So I begin with the empty sequence up here, and then I draw these trees. So there's this 1, 0, 1, 2, 3, 4, and so on. And each of these guys now gets another bunch of trees, starting at 1 this time, and so on. So I'm building this tree, and this tree is where we will I will do most of the argument. So this will be the picture, the mental model that I want people to have. What is the picture for h equals 2? For h equals 2, equals 2, this corresponds with I have certain guys down here that I've colored red. Okay, the other ones will be colored yellow, but I only color the red ones for now. And these correspond with 2, 3 is the edge in the infinite graph that is colored red. Right? 2, 5 in this case is not colored red, so it's colored yellow. So the coloring of the graph corresponds with me coloring a bunch of points on the second layer of this tree. Does this make sense? So again, so in the previous proof, what was I doing? I was restricting every step, right? I think of that proof as a cutting down proof, right? At each step, I'm only restricting my attention to a certain nicer subset, and at the end, I get this string that is already fully formed. So this time, I build from the ground up. The previous proof was cutting down, and this one I'm building up. Let's see. Oh, click on build. A, which I'm now thinking of as a sequence, an increasing sequence, okay, by S0, which is the empty sequence, initial segment of, this is my symbol for initial segment of, S1, initial segment of S2, and so forth. So I can build this infinite sequence A by looking at finite sequences at the beginning, and just building up one element at a time. So for things where I increase by one thing, like if I have the sequence 2, 3, 5, and I append 6, okay, I'm going to call that an increment. Okay, so if I increase the sequence by 1, I'm going to call that an increment. So let me just give you some more notation. Not that take much more at this point, but n to the less than infinity are the finite sequences of natural numbers. Does this make sense? Okay. So why is building up hard? It's hard because let's say that over here in this subtree of 4, all of them are red. Okay. And now for this model, okay, let's try to avoid the red points. Okay. So from this part of the presentation onwards, I'll be using language that reflects the fact that my goal is to avoid the red points. So what happens if this subtree of under 4 is all red? Then I'm screwed if I choose 4, right? If I choose 4, it seems fine, but I'm already dead. Okay, I'm already dead. So we must have some way of sort of preemptively warning people that there are a lot of red points down the road, and you should not go down this road if you want to avoid these red points. Okay, so building up is hard because of the fated to die problem. I choose wrong up here. I don't know it, but 5 steps down the road, I'm dead. Okay, so I must have some sort of advanced warning system. I want to have a warning system. Or you can also think of it as sort of the red points are bleeding upwards, right? If there are a bunch of red points here, then somehow 4 should, be a little red to indicate that, red things are on this road. Yep. Okay. So I now have to unfortunately introduce the concept of ultrafilter. Which, for those of you who were here before last week, were already introduced. Okay, but I will not use the word ultrafilter. For pedagogical reasons, I will not use the word filter. Suppose I have a notion of big. Or most. In particular, okay, so if I have A subset of B, and A is big, then B is also big. That's a no-brainer, right? Now here's the kicker. If I have a big set and I intersect with a big set, that will also be big. Okay. And for all A subset of natural numbers, okay, exactly one of A and A complement are big. And the other, of course, is called small. Well, it's quotations. Okay. I don't think I'll be dropping the quotations anytime soon. So for those of you in the know, this is the notion of an ultrafilter. But it will help us because exactly the problem we want to, have some control over is, are there very many red points down the road? Okay. And very many in this case will be quantified by this notion of big. You may ask, does this exist? Okay, we won't talk about it. Okay. By the axiom of choice, you can, by Zorn's lemma, you can build one of these notions on the set of natural numbers, but we will ignore this technique. And now I will define notion of alpha doomed. Okay. And this is very, I think, self-explanatory. If I have a sequence, a finite sequence, I'm going to say that that's 0 doomed if S is already in the set S of red points. So if I'm already in S, I'm doomed. Okay, it's like, yes. Okay, now for alpha, okay, I say that S, a finite sequence, okay, is alpha doomed if most increments S concat n. Okay, this is the symbol for concat. It's 2 pluses stacked next to each other. It's Haskell notation. Most increments are beta doomed, or beta less than alpha. Okay. So if a bunch of guys, if a bunch of guys below me, okay, that's increment is below. Okay, bunch of guys below me are doomed, then I'm also doomed. Okay. Yes.
So let's be clear on the order of so I want to be clear on the order of quantifiers. So I'm guessing is this something like, so for most n,
Okay, hold on.
there exists a beta less than alpha.
The n such that S concat n is beta doomed, or beta less than alpha is big.
Wait, but there is an existence sign for some, yeah, okay.
Okay. So do you understand the intuition? Or yes.
Add that finite sets are small.
Yes. will be very, very important. Get up. And yes.
Sorry, what is capital S when we say something zero due and little s?
So S here is a set of red points.
Oh,
Okay, so I want to avoid the red points S.
Yeah.
I'll color in the color red. Okay. Great. So let me try to look at this picture. Over here, all of these guys are zero doomed. And this guy is one doomed. And the rest of them, maybe they're, oh yeah, I forgot. They are not doomed if not alpha doomed for all alpha. Okay. Really self-explanatory, like I said.
Are we thinking alpha to be like an ordinal?
Please. Yes. Pretend you didn't hear that. Okay. And now I complete the h equals 3 proof. Okay. Why not h equals 2? It's because it sounds really bad in this language. Okay. You'll see. Okay, let me see if I can. That's very unfortunate. Okay. Okay, so case 1 is the empty string is not doomed. Okay, which intuitively means that there's a lot of stuff underneath me that will not lead me to dooming. Okay. Okay, so S0, I'm going to find the empty sequence is that, okay. And now suppose I have S0 all the way up to Sm, okay, where each of them is an increment of the previous. Okay, so I'm going to prove this by induction. Suppose I already got S0 through Sm such that all subsequences of Sm, okay, let's see, of length 0, 1, and 2, okay, for h equals 3. For h equals 2, the subsequences are really boring. Okay, so for h equals 3, all subsequences of Sm are not doomed. Okay, and my goal is to now increment it to the next guy up, so that that is also so that all the subsequences of it are not doomed. Okay, why do I care? Not doomed means in particular, not hitting a red point. Okay, so in fact, not even close to hitting a red point. Okay, but what I really care about is hitting the red point. But I have to define this notion of doom to not even hit the red point. Okay, so let M0 and SMQ, Q for subsequence, subsequences of SM of length 0, 1, and 2. Okay. So in this picture over here, suppose I have SM. Suppose I have SM is equal to 3, 5, 8, and 9. Okay, that's my subsequence so far. Remember, my goal is to build up A, which is infinite, right? So I'm pretty early on in the process. Then SM0, SMQ are everybody like empty 3, 5, 8, 9, 3, 5, 3, 8, and so forth, right? You get the picture. Okay, so there's finitely many of them, okay, Q of them, or I guess Q plus 1 in my numbering. And then my claim is that for all I, okay, most increments SMI concat n are not doomed. Okay. Your intuition, you shouldn't be too surprised that this still needs a proof. Maybe I should define something, i.e. VMI, the set of all n, so that incrementing by n is not doomed, is big. Does this claim make sense? Okay, my proof, suppose not. Okay, suppose not, then for most n, indeed SMI in cat n, okay, is doomed for some alpha, right? It's alpha n doomed. In my setting here, this is not terribly interesting because in my setting, alpha n is at most 1, 2, or 3. Okay, so 3 layers down, something is waiting for you. Okay, okay, but then recall the definition of doom. S concat n is beta doom for beta less than alpha, right? So then S wait a minute, SMI must be alpha doom for alpha equal sup of this, right? Right. By definition, right? This guy is doomed because most of its increments are doomed for beta less than it.
But if you're using less than or equal to, you're using 2 plus 1.
Okay. Okay. And I guess that everybody below this is also doomed. Okay. Do I need that? Maybe I don't need that. But does the claim make sense? Right. It's just using the definition. Okay. So I get VM0 through VMQ, which are what? Which are big. And so take their intersection, right? That's also big. The intersection also big. Okay, which means, in particular, there are infinitely many elements of it, right? CF, finite sets small. Okay. So, pick n from the infinite intersection. Okay. And then my claim is that Sm plus 1, Sm cat n, is still not doomed. And in particular, and all of its subsequences are also not doomed by construction. Okay. In particular, it also does not hit the red point, right? It's not doomed, so it also doesn't hit the red points. Yes, no, question mark. Okay. And so we have constructed our set A. Okay. Case 2 is very similar. It's the case that the empty sequence is alpha doomed for some alpha. In this case, 0, 1, 2, 0, 1, 2, or 3. Okay. And let's see, maybe I can give it 2. No, I think I'll try to extend this first. Okay, maybe if I have time, I'll cover case 2, but I promise you it's very simple. Okay, very simple. Okay, so now I can state the correct statement of the infinite Ramsey theorem, which I will finally give a name. It's called the Galvin-Prikry. And I've seen it referred to as sort of the jewel of infinite combinatorics, infinite Ramsey theorem. Okay. One of the more pretty, more elegant, beautiful results. Okay. As many applications in weirdly Banach spaces, people construct very weird Banach spaces using the Galvin-Prikry theorem. Okay. In fact, some of that work led Gowers to win the Fields Medal in 1998. So it is relevant in other parts of mathematics as well. Outside pure math, I don't know. Okay. So what is the statement? The statement is, let's see. I think I'll just have to resolve it. The infinite theorem says that if I choose any countable set S of red points in this tree, any countable set S of red points, then exists an infinite sequence, or you can think of it as in, and choose infinity, okay, such that all subsequences A choose infinity either avoid the set S or all pass through. Either you always avoid or you always hit. Okay. And I have literally given you the proof. Okay. The only thing I have to change is the word ordinal. And then I'm done. Okay. And you ignore the green bits. Okay. Then I'm done. This is the proof of the Galvin-Prikry theorem. Okay. I will do case 2. Yes.
So you have like your case one.
Yeah, the case 2 is coming. Any other questions?
There's still an issue with the soup or?
No.
I guess-
It's the ordinal soup. We're fine. Okay, actually, this is a good question. Why do I need ordinals here? Why do we need ordinals? Okay, here's the following picture that explains why we need omega good. If you don't know what ordinals are, hopefully this will teach you, or at least give you some working experience. Okay. So suppose I have the following. This is the empty sequence 0, 1, 2, 3, and so on. Okay. And now 0 itself, I'm going to color red. Okay. 1, I'm going to color all of its guides red. Okay. And then 2, hold on. Yes. 2 has a bunch of children, right? And I'm going to call all of its grandchildren red. And so each guy, so 1's children are all red, 2's grandchildren are all red, 3's grandchildren are all red. Okay. So these are 0 good. What is this guy? All of its children are 0 good. So it is 1 good. Sorry. Please forget. Doom. 1 doom. Okay. And 2 is 2 doom. Right. And so I will need to so if I continue in this way, then the empty sequence will be omega. And now you can imagine that instead of having this at omega, at the empty sequence, now I put it in a small subtree. And I keep having more and more of these subtrees. Okay, then I can have omega plus 1 doomed. Okay, which means I'm doomed in omega plus 1 steps. Yes. And so actually you will get, I don't know how high in the ordinal hierarchy you could get, but maybe epsilon 0 or something. Okay. Any questions about the notion of in this infinite setting. Okay, so I will fulfill my this. Probably, like, I don't even know if you can state it in PA. So, yeah, there are definitely very, very hefty infinitary methods being used here. It's fully within the realm of logic. I took this directly from Andrew Mark's 223D class, right? Which Mark can attest. Okay, any other questions before I try to do case 2? Okay. Let's see. Case 2, I think it instructive to rename all of my terminology. Because the goal has changed, right? The goal is no longer I want to avoid the red points, but now I want to hit the red. So I'm going to rename alpha doomed to alpha good. Okay. Okay. So case 2. Case 2 is that
Do you call it not good or bad?
yes, I call it bad. Okay. So suppose the empty sequence is the opposite of that case, which means it is alpha something, and the change language is alpha good. For some ordinal alpha, you can think of alpha as omega plus 1, just something, so that there are eventually a bunch of red points down the line. Okay, very far down the line maybe, but down the line maybe less. Okay, then similarly make a sequence S0 SM. Okay, I build it up. What's it called? Inductively of good sequences. So if okay, maybe I'll say that such that to match the language over there, such that SM compact N such that SMI subsequence of S, okay, then either SMI is 0 good, or in case I actually hit a point of red, so I'm happy in this case, or SMI is alpha good, and SMI cat N is beta good for some beta less than alpha. Okay, so again, just my inductive hypothesis, right? Exactly sort of dual whatever happened over here. Then this case is actually even easier. Any decreasing sequence of ordinals terminates. And so if I have a bunch of alpha good sequences, so that the next step down, right, I have to choose one guy underneath to continue my story, then that's a decreasing orbital. I start at alpha and then I choose beta beneath me. I choose an increment, and that is necessarily beta good for some beta underneath alpha. So I get a decreasing sequence of ordinals. And any decreasing sequence of ordinals terminates. Right? And anything bigger than 0, I can keep going down, and that terminates at 0. And so I have concluded that any subsequence any finite subsequence, okay, any subsequence of Sm which is finite, eventually hits zero. Sorry, eventually becomes zero good. In other words, eventually hits a red point. And this is true for all finite subsequences. And when you hit a point that is witnessed within finite time, okay, and so I've proven that indeed by this construction, everybody passes through one red fever tree. Does somebody want to answer? Sorry, ask any question? Yes?
And also, guess that question, I'm actually also not sure what's going on the earlier case about the series, so. You were saying, so the sequence of eventually, how do we get so like, how do we get this homogeneous set from like this argument, but.
So from this argument, I'm making it so that I can always choose, and so that I'm not doing it. Right, so I will never get even close to hitting a red point.
Okay, so you're choosing okay, so this is an infinite sequence.
Infinite sequence A, so that all subsequences will not hit any of the red points.
Okay,
Perhaps, let me do one thing.
wait, maybe I'm missing something about, like, it is the point that, like, it. Wait. I'm a bit I'm sorry, go on.
Okay, in the back.
I was going to ask, how are we defining pass through? Is this?
Pass through as in like,
Okay,
this, a red point
there's-
is a sequence, right, corresponds with the sequence. And it passes through the red point if the initial chunk of it is the same as what I need to do to hit the red point. So pass through as in, if I walk along the sequence, starting at the empty string, then I will hit that red point at that spot.
So. Are we passing through arbitrarily many red points or just?
I don't have to, I just need to pass through one. That's the statement of the theorem, right? Pass through some, sorry. Pass through some point in S. That is the correct statement. I don't have to pass through all of it. I just need to pass through one. Yes.
So that, okay, for like two graphs, like the red points are all above. Right?
Yeah, for h equals 2, yes.
So for h equals plus infinity. Like. Here are the red points, like.
The red points are any countable set of red points in the tree. So I can just choose, like, there's a bunch of vertices in the tree, right?
Yes.
I can just choose a countable number of them to be colored red. So it's a generalization.
Oh, okay, I see.
It's, you know, in the h equals block case, all my red points are on a certain level.
I see.
But in the countable case, I can put them anywhere.
I was still thinking about that.
When you see that function countable, like, isn't the total number of vertices in the tree countable by itself?
Maybe, I don't know. Maybe you can ignore that. But, okay, I just mentioned one thing. If you topologize n to the n, okay, so hold on. I have that n choose infinity is in bijection to increasing subsets or increasing sequences. Increasing sequences are obviously a subset of sequences. And you can also think of an infinite subset as a function from n to 0, 1. 1 is in the subset and 0 is not. So you can think of this as also inside of the inside of PDN. Right, I think that's the correct notation. And both of these guys are, you know, if I endow 2 and n with the discrete topology, then this I give them the product topology. And in fact, it reduces the same topology on this guy. And this statement up here that any countable set S, I can replace as any open U in the topological space now. And choose. And avoid S would mean avoids U, and passes through S means lives inside of U. So this is because any open set U in this topology, the topology is given a basic opens are things that agree up to a certain point and everything else is free. Right? Those are the basic opens in the set. And so choosing a red point is choosing the tip of that tree where, so the open sets in this picture are exactly these guys. Okay. And so a sequence belonging to U means that eventually it goes inside this cone. So yeah, the statement of the theorem is a little cheeky, but if you want to be more fancy, this is saying that any open U in this thing, there exists an infinite subset so that it either avoids U, in other words, A infinity intersect U is empty, or A infinity subset of U. So if you like that wording better, by all. I will say that actually what Galvin-Prikry proved was that for any Borel U in the set, this is still true. But the hard part of the proof is, in fact, the open sets. If you go to Borel, it's apparently easy. I say apparently because I never got around to figure that out. Because Andrew only taught us the open case. Okay. Any questions? I still have 3 tangents I can make, but if people want to, I don't know, is it time? Can I say one thing? One reason that I really like this proof is because, or these Ramsey theorems in general, because they're dichotomy theorems, right? You want to prove one of 2 things. And I think in math, this is kind of hard because maybe you're used to proving one thing. But how do you figure out, which cases go up here, which cases go down here? I think this is actually very interesting. One of the first results that I found very interesting was the Spanish hotel theorem. Or I'll tell you this one actually, but the very basic theorem in real analysis that says that if I have any sequence xn R, either exists a increasing subsequence or decreasing subsequence. Right? Very common in real analysis. Maybe you even taught this at one point. But the proof Clark told me was, like, the difficulty is, again, how do you push into one of the cases or the other? Like, you have to have one differentiator. I call it a dichotomy differentiator that pushes you one way or the other. Okay, so what is Clark's thing? Why is it called Spanish hotel? It's because if I plot all the xn's, right, all the xn's I can plot like this. Okay, then the dichotomy differentiator is: are there infinitely many hotels with ocean views, where ocean is this way? Okay. So if there are, that means that this guy has an ocean view, so everybody in front of him is underneath, right? So I can just keep going, right? That's my infinite decreasing sequence. Whereas if there aren't infinitely many hotels with ocean views, then I get my increasing sequence. So I saw this before, and I was like, wow, that's so smart, that's so cute. And so all of these theorems, right? What is the dichotomy differentiator in this theorem? It's this notion of alpha good. Right? So you just have to come up with very clever differentiators and you get amazing output. That's it. I'm actually done.